there on Facebook. Tell him. What are you doing at home? I'm sure you can put those marks on Blackboard. So my general hint for this week is, all right, if everyone's got this hint and understand the hint, you better make sure you know how to graph simple diagrams for this week's quiz. All right, because without that bit of knowledge, you might be losing 4 marks. There are 2 4-mark questions there. All right, so there's going to be quite a lot if you don't attempt one of those. Anyway, that's my bit of advice round for today. Drop-ins are always there. Redemptions, all right, we haven't got as many redemptions as we could have. Let me just put it that way, because we can always have more redemptions coming past us. So remember to get those redemptions in. If you're at home and you're not in on a Friday, if you can scan it, send it to Dave or I, we'll still take it. So we're happy to take a redemption no matter what. And we are turning the corner into exponentials and logarithms. Now, exponential and log functions, we're going to search this out today. I don't think we'll take the whole 2 hours, I'd imagine. So Dave trimmed this one down. Last week, we had a bit too much work. This week, it's a bit trimmed down. So I've got some extra questions to ask you. If we get time, I think we should. So here's what we've got. Okay, is everyone okay with where we are? I think we're on about page, round about page, we must be on a 50-something, a 54, alrighty, a 54. Grab your calculators out as well, because there'll be some calculations needed. Righto, here's a few reminders, guys. 124, exponentials. You know the general shape of it. There was a couple of details. Keep this in mind. We do exponentials this week. We do series and sequences in A6, so you might remember APs and GPs. And then when we do B1, we go into trig, and exponentials come back to us in B2. Okay? So there's a bit of a gap between this and the calculus of exponentials, but I need you to start thinking about what these exponentials used to look like. So back in 124, it says y equals 2 to the x, and it had the values there, and you remember that if you had a 2 to the x, it was at what we called an increasing. It had its y-intercept there. It had an asymptote on the 0 there, so I'll just do a quick little dotted line, which means it approaches 0 as you go down that way. This is an exponential. It said if you put a 4 in front of that, what does it change? It changes the y-intercept, but it doesn't change the asymptote at all. So this is leading us to reminding ourselves, all from 124, okay, all from 124, that this was the increasing version. So if this value was a 2, you'd get the increasing version. If this value was a half, now a half can also be written as 2 to the minus 1, okay? So both of those are the same graph, because a 1 on 2 is the same as a 2 to the minus 1 to the power of x, which then makes it look like 2 to the minus x. So these graphs are decreasing, coming down. So both of these are trying to be embedded in your head. All right, you've got the increasing version, and you can tell when you get an increasing version, you've got the decreasing version happening, okay? So this is what ends up starting as. This is on your page 54. An exponential function is of this particular form. So now we're starting to use this a equals a0. That's like an initial amount, okay? So then it says this initial amount a0 being multiplied by m to the power of t. So it's got the same sort of format as what we had in 124. So we've just changed, all right, a few of the variable names. So it basically tells you that that capital A will give you the amount after time has gone past. Now that t can be in seconds, in days, in months, in years, depending on what the problem is. This guy here, this A0, will always be the initial amount. Now they may put that in one of your clues, so your job is to say, oh, that's actually being handed to me in a different manner, but I know that it's the initial amount. And comparing it to the graph, again it's saying the initial amount would pop up on this particular axis. You can see we don't have the left-hand side of this graph. Would anyone like to tell me why we don't have the left-hand side of this graph? What's happening on that side of the graph in terms of the variable t? What would t it'd be? Negative. And we don't have negative time. So although this has been chopped off, what it's making you aware of is that it was an exponential function and it would have kept going down that way. So this is the initial amount coming up on the p-axis. Now, I think he wanted the a-axis there, so we'll cross that out and put the a-axis. What's he got in the book? Has he got a p? He wants an a. Quite often, you often will see these questions, and the reason why he's got a p there is quite often you will start with p for population. You might also start with n, all right? So it gets written down with a different batch of letters, but every time you write it, if you're finding an a, there's always an a0, which is an initial amount, okay? So this m is the multiplying factor. Now that multiplying factor, we're going to establish that in some of the earlier questions, and in some of the questions it'll be given to you. So this says, take for example, an initial value of 10. At this point, if I had to, I'd stop and say to myself, initial value, this seems to be telling me the clue that a0 is 10, being repeatedly increased in value by 20%. Start with 10, increase it by 20%, get a new number. Increase that new number by 20%, get another new number. Increase that again by 20%. So this keeps happening to it. So then your job is to take this clue and realise that the multiplying factor, okay, will have been 100% plus 20%. So that's why they've given themselves a multiplication factor of 1.2. Now sometimes it's going to go up by a percentage and sometimes it's going to go down by a percentage. So your job is to listen carefully to the clues, because in next week's quiz, all right, if I give you a question, I won't be giving you the starting equation. Your job will be to come up with a multiplying factor and then to put the equation together. So you're always looking for an initial value. You're looking for a, how do I get the multiplying factor, okay? And then it says, when t equals 0, this is actually what was happening. Again, he's put p down there, but he does mean a in there. So a is equal to, and then he's got 10 times 1.2 to the power of 0. So he's established himself with an equation that a will equal a0 m to the t. So I'll put here 10 times 1.2 to whatever the t value is. And t started out as 0, can't be negative. Then he started to go up to the t equals 1, and he puts it into the formula. He gets his new answer, and he's just graphing these values. But you should have known that it was going to be an exponential growth, because as soon as you see this value, all right, as soon as you see this value, all right, your job's to remember 1, 2, 4. When is it going to be an increasing exponential, and when is it going to be a decreasing? So you could have said to yourself, I knew it was going to start at 10, and I knew it was going to be an increasing function. So over to us. This is down with you on page 54. Construct exponential equations for each of the following scenarios. So this is up to you. What I will do is over here, I will start with the one that I would walk into my quizzes with, which looks like that. A is equal to a0, which is the initial amount, times by m, the multiplying factor to the power of t. So what will we put here? The clue says initial value of 100. So straight away, I think a0 is 100. So I won't forget that. I've put that down and I've locked that in. It then says that it will be increased. Now you'll be amazed at how many people will miss that word if I put it in next week's test, because I'll either put increased or I'll put decreased. So increased by 6%. So straight away, I'm writing down that it was 100% and that it went up. That's why I put a plus. And I've got 100% plus 6%. That gives me a multiplying factor of 1.06. So that's what that's told me. Okay? I found my a0. I found my m. I think I can find the exponential equation. So it says a will equal 100 times by 1.06 to the power of t. That means I could use that now, okay? And that t, by the way, I'm just going to emphasize here that t is in days. All right, because they said 6% every day, I'm going to establish that at the very beginning, because what we do is get very sloppy at those fine details. Because I might try and trick you and say, you know, let's just say if I asked you, what's the value after 1 year? A lot of people will put a 1 in there because they think the T is in years. But if the T is in days, the 1 year would have to get converted. Okay, so I'm going to stress this every time I establish, all right, an equation. Round 2 says, again, you're constructing your exponential equation, and it says initial value of 50, so I'm going to write A0 is 50. I'm going to have written down this in my, I guess, on my resource sheet to bring in with me. A0 is 50. This time it's being decreased, and I make a big effort of saying, make sure you go down, so that when you get this particular multiplying factor, again, I start at 100%, but I come down by 12%. Right? So I've put that extra bit of working in there because when I look back at this, I don't have to scratch my head to see where did, and I'm about to write 0.88. But anybody that just puts 0.88 in a week, in 2 weeks, or in 3 weeks, you might forget how you got that 0.88. So it's really worthwhile to put down how you got it. And then when you establish the formula, it comes out as 50 being multiplied by 0.88 to the power of t. And again, I'm just locking in that t is in days. So your time factor, all right, has to be in days. So there's a couple of those questions in your tutorial when you have to practice. So again, where are the potential places for me to grab you? The word increased or decreased, all right? And I might get you on that time factor, checking out whether you're paying attention to your t values. All right, next thing says applied exponential growth. So it's just giving you some examples of where this might pop up, all right? Exponential growth. Population growth of people, animals or bacteria, so you're going to see these questions in your tutorial. Compound interest is also an example of it. Sometimes the growth of a flu or a computer virus and how it gets sort of out of control. The mass of a tree trunk, places like the area of a bushfire grows exponentially, so they try to model it, okay, when they know they've got this happening. Now you can see that the only thing that's changed here when it comes to population growth is they've just changed the letter. So instead of it saying A equals A0 with an M to the power of t, you can see that it says P is going to be found, which is population at time t. P0 is again that initial population, and this time A is a constant, is what they've said. Okay, so A is a constant. So, again, the graph of it looks very similar. You can see why it doesn't have the left-hand side. You can see why it pops up here. Now, all of these are going to be crucial when we come back to these, guys, in about B2, I think I said, B2 or B3 lecture. So this guy says, construct an exponential equation, all right, for a population of 16 rabbits. So I think this has been my initial population. So straight away I tend to lock that in, which is expected to double every month, all right? So when we say we're about to double every month, what do you think that, I guess the multiplying factor, all right, if it's going to double every month, what are we going to take from that? Double every month. So it says there, you've actually got it on page 55, it says here's the one I usually walk in with, and I fill in what I know, the initial population and the multiplying factor. I've got my 16 in the right place, I've got my 2 to the power of, and the only other thing I'd stress is that t is in months. So just make sure you're aware, because again, in a question, I might throw something at you, and if t is in months, but I ask you for a year's time, again, it's about trying to catch out who's not reading the fine details in their question, okay? And it looks like this going up, right? Again, initial value you see and then plotted, growing quite severely. Turn the page over and it's got population of a town of 10,000. So straight away, I'm sort of locking in that I think this is going to be my, and if I don't want to use A and I want to use P, P0 is going to be 10,000, locked in straight away. But I am very cautious because it says there was 10,000 in the year 2016. So I've just put a box around that for a minute. Is expected to increase by 6% per year. Now it says construct this exponential equation for the predicted population, and it mentions after 2016. So basically 2016 gets taken as base of 0, I guess, like the 0, the starting point. So 2016 is when t is equal to 0. We're starting from that. So when I go to say 2017, I don't enter 2017. It's not 2017 years that I want to put into the formula, because it says here let t be the number of years after 2016. So these questions can trip people out as well. Now our job was to construct. So first thing is on the side, this is what I've walked in with. I've walked in with this. Now you can put m, if you still keep writing m, I'm not going to penalise you. So you can put this multiplying factor, or you can put that a value. Alright? So you can put that, or if you're thinking still with this a value to the power of t. You know what your P0 is? Alright, we didn't come up with our multiplying factor. So the multiplying factor would have been 100% plus 6%, and again, the reason I write that is so that people can see why I get 1.06. So it turns out to be P will equal 10,000 times by 1.06 to the power of t, and again I'm just pointing to that t because I want to make sure that I've established that t is the number of years after 2016. So 2016 is the starting point. It's the t equals 0. We right with that? Establishing that and just talking to yourself so that you don't trip on that t value. So the second part says, calculate the population in the year 2024. So I'll just bring back that we had P equaled 10,000 times by 1.06, and we had T, and we were pointing to the T. This was still just on the last slide. T was, make sure you enter T as the number of years after 2016. So I can obviously see that that equation is pretty simple as long as I know what T is equal to. Now the problem is the people that write 2024 straight in there are going to get a different answer. But it wanted the number of years that have gone by since 2016. Any suggestions to how many years have gone by? 8 years have gone by. Now there's going to be a very different answer. People that put 8 in to the people that put 2024 in. Okay? So it's an 8 that I'm substituting. So again, I like to show my substitution because you'll be amazed at how many people will make mistakes on the simplest of things. So even when they go to pick their calculator up, all right, and they go to push things in, if I can see that, you're going to get some marks from me because you had the right intention. You were actually walking away to the calculator with the right thoughts in your head. Now the next thing that happens is I get a number. It better have increased. This is another thing people don't pay attention to. If this number has not gone up over 10,000, you must have made a mistake somewhere. Now I'm pretty happy. I'm looking at 15,938, and I will just put 0.4075 because that's what it's come out as. Anyone else get that number? Yeah? So that means that I'm going to probably round this off to the nearest whole number, which is going to be that. And I'm just going to say to the nearest whole. Question said calculate the population. So I think 15,938 sounds like a reasonable answer to the population. But I do pay attention. I listen to myself because I'm hearing whether this should have gone up or whether this should have gone down. And things can happen when you go to the calculator that you never expected you to do. We do make mistakes. Question says how many years? Now as soon as I see how many years, I actually stop reading and I realise it's asking me for a t value. So this is saying how many years, which has already started differently. This is going to involve a little bit more mathematics. How many years will it take for the town's population to double that of the year 2016? So let's get this clear. In the year 2016, which is when it started, the population was 10,000. We got told that at the very beginning of the problem. They want population to double. They want it to be double that of 2016. So that means I want 20,000 to appear as the population. So this is a question of, in 124, so think carefully back to 124, all the skills you learnt back there was a lot of equation work. And I kept saying to my group especially that we were really no good at equation work, because this is saying, I'm now handing you P, your job is to find T. Now as soon as that pops up, I go back to my original, which said, this is what the original said, times by 1.06 to the T. Now if I'm being told P, that's going to go in on this side, and what it is I'm looking for is the T value. Can you see where the T value is? It's up in an index. Can someone start preempting what kind of equation do you think we're heading into, or are we in? What kind? We're going to need logs. We're in an exponential equation, and we're going to need logs to actually work this out. So this is a little bit of 1, 2, 4. So here's me substituting. Now even that gets you marks in a quiz, because at least we know you put in the right number and you put it in the right place. Now your job is to solve for T. So the first thing I do, and by the way, these are all really crucial small details. There are people that would love to do this, but order of operations does not allow you to multiply those two. So you can't actually multiply 10,000 by a 1.06, because this guy is involved in its own little world. So the first job is to divide by 10,000. So dividing by 10,000, you'll end up with a 2 equals a 1.06 to the power of T. So that's again a bit of equation work. Now again you might get to that spot and say, I don't remember what to do. How do you bring that T down? And we had a suggestion down the front to use logs. Now, doesn't matter, there are two buttons on your calculator. One's log to the base 10 and one's log to the base E. Does it matter which one you use? At this point it doesn't. So when I put log, everybody knows that I'm putting that to the log to the base 10 on this side and log to the base 10 on that side. Now I write that line down because it's the tool that lets me bring the T down. So the T now appears down here. The T now appears down here. And when you go to make T the subject, you are dividing. So T to be made the subject has to be divided by, and I've just swapped sides, so I hope nobody has been confused by that. I've just swapped over the sides. So T is equal to the log of 2 divided by the log of 1.06. Now when you go to your calculators, please make sure that you have the fraction first and then the word log, because I'll tell you another minor mistake. There are two log words there. This answer is not the same as the log, and people will think, can I do that? That is a completely different question. So when you go to do this on a calculator, make sure you bring the fraction button up first so that you don't make this mistake, okay? So that you can actually put the log of 2 on the top. Another lesson, they like the, on these calculators, they like the brackets to be closed. Otherwise, it's just another time-consuming problem because it'll say math error and all you did was not put in a bracket. Anyone getting about an 11.89? Okay, so here's the thing. I'm coming up to this answer and I'll put 11.89566 ... So something like that. Now what was this in? What was this in? What was the T value established in when we started? Years after 2016. So I'm going to say I will approximate this to the nearest whole number, I will say 12 years, and I'll put here to the nearest whole number. Now that is 12 years, and I will just stress to myself, after 2016. The question only asked you how many years, so you're okay in stopping at 12 years. But sometimes our questions in the tute might say, during which year did that population hit the 20,000 mark? All right, so during which year is a slightly different question. This only asked how many years will it take, okay? So that's that question out of the road. And then it says how many years, because this is the fourth part. Again, I circle that and say to myself, they want me to find T again. And this time it says, will it take for the town's population to double that of the year 2024? So your answer back in 2, okay? So back the population in 2024. What was our population in 2024? Can someone call it out for me rather than me go back to that slide? Oh, hang on, it was a 15,000, wasn't it? So it was a 15,938. Check on that number, whoever called out the other one. And again, the question says, how many years will it take for the town's population to double that of 2024? All right, so again, you can start with this information. Start with the initial one, which said 10,000, and then it said times by 1.06 to the t. Now again, by us putting this in again, it's getting you to practice your exponential equations because you haven't done it for a while. So what you're doing is saying, I'm going to put 15,938, put the 10,000 times by 1.06 to the t. Now I won't get such a nice pretty number like 2 anymore. And again, we're trying to trick people because I guess people see the word double and they think that there's going to be a 2. But this was double the population in the year 2024. So again, first thing is divide by 10,000. And again, what I've got here is 1.06 to the t. Dividing by 10,000, 1, 2, 3, I'm getting a 15.938. Now I don't tend to say... I don't tend to round my numbers off until the very end. So it's a lesson you learn from, when you start maths. You never actually approximate until the end. Otherwise, you're creating problems along the way. So don't round that off because you can't be bothered to write it all in. Remember, these calculators have that answer question down there, answer button down there. So it's going to do a lot of reminding for you. What can it do for you, Justin?
Why did you double the population of the year 2024?
Oh, I didn't double it, did I? Oh, thank you, Justin. It was that number that we put out there. So hang on, get rid of all that. Get rid of all that. And then that guy there, 15,000. Much better suggestion. Justin, much better. So this guy here should have been 31,876. So there's a 31,876. Because I was actually concentrating on this because I was trying not to get people trapped in the obvious, which is put a 2 there because they hear the word double. But it's double the population of 2024. So this guy here should come out to be a 31.876. And I was still just reminding you, don't round things off until the very end. So just try to remember one round of approximations. You are now taking the log of both sides. So again, some people need to see the reason why logs have come back into your life is because the only way you can solve an exponential equation, which is what this is for you to use the tool called logs, okay? Yeah, Alex. Oh, gee, it is indeed. So let's put that there. We would have had a great number to come up with. All right. I could blame my glasses. I'm still trying to get used to these, but it's not that. It's just a bad day, I think. So the reason why I'm putting the logs there is so that that t can come down. So this is a t multiplied by the logs of 1.06. Or I could say that I'm checking whether you're all awake. That could be another thing I could say. I'm dividing by, so here it comes, I'm dividing. I tend to swap my sides over, but I'm very cautious on, I am dividing by the log of 1.06. On the top it's the log of 3.1876. Again, just that crucial small detail. When you go to the calculator, make sure you have log on the top and log on the bottom. Make sure you close those brackets. They're all small details, but in an exam, you know, people will say it's taking me too long, sometimes because we're making small errors that the calculator says, no, do it again. Did anyone get 19 point? Anyone getting a number like that? 19 point? Alex is nodding, so I'm going to go with that and say 89514 ... And again, it just says how many years. This is in years, but we could round it off. So you make a sensible approximation that this could be 20 years, and I've rounded off to the nearest whole number. I tend to remind people that if I've done an approximation, which is a rounding off, that's an approximation, I tend to tell people what I've done, because people can still make a mistake. Because if I'd said this was to 1 decimal place, okay, then it should be to 1 decimal place, it should be 19.9. If you don't get 19.9, if you by accident give me 19.8, 19.8 is not correct to 1 decimal place, and it's not correct to 3 significant figures. It's not an actual correct approximation. So anyone that makes a mistake, you see, like that, they're not paying attention to what it is they should have been reminding themselves of their approximation. So that's why I do that, because no matter what, you can still make a mistake in the rounding off. You're allowed to choose the rounding off in that sort of question, by the way. When they don't tell you, you can make your own approximation. So they're the things growing, okay? They're the things growing. They are there's one thing that is in the book. One thing that is in the book that down here, all right, that Dave has put, but it's going to be pretty hard to say. See at the bottom of page 56? An exponential growth function will have a fixed doubling time. Do we agree with that statement? We don't agree with that statement. So have we made a mistake? Did I do anything in there that was wrong? Because I'll have to come back. It's not on the slides. He hasn't got it on the slides, but it's at the bottom of page 56. So I will make a little comment. I'll come back to that, and then I might put it up on Blackboard. Which one was it? Why isn't it 10,000 though? But that's us establishing a new equation and then taking time of, now hang on a second, it's just because that's years after. This guy here is the number of years after 2016. So if it's 20 years after 2016, then it would have happened in 2036. So if this has happened in 2036, that's the year when the population got doubled, and then that would agree, would it not, that it took 12 years? Can you see what I mean by that? So that when down the bottom of page 56, because it's not on one of the slides, he's got an exponential growth function will have a fixed doubling time. So when we asked in part 3, when we asked what was it to double that original population, we said 12 years, all right? So it's taking 12 years. So where I just got, when I thought about it, I thought that doesn't sound right, but I had to reinforce the fact that this is 20 years after 2016, or Ash is suggesting that if you did that question, you would have changed your P0. So that would have given you, again, a 12 answer. Yeah. Yeah, so you could have changed the initial answer, the initial population. But both ways, yeah, they both now prove the bottom part of page 56, which says an exponential growth function will have a fixed doubling time. So it takes 12 years for the population to double, no matter where you are, okay, in whatever year you are you start, it takes 12 years for the population to double, okay. Round the other way, applied exponential decay. So decay is going down, all right? So these are the graphs that, when we introduced it to you before from last semester, these are the graphs that are going down like that, all right? And it comes up in things like cooling temperatures. They might pop up in some of your science areas. Radioactivity, depreciation, which is usually about your money, or even cars depreciate. The slowing of a pendulum, the intensity of light in water. So these are some areas that it pops up. And again, we don't go into too much of the physics behind it, but it's talking about Newton's law of cooling. But don't panic, because not everyone does any sort of science in here. You don't have to. It's basically coming down to the same idea, and this time they've used a capital T for temperature. So capital T, temperature, will be the initial temperature multiplied by this A. Again, you can call it a constant or a multiplying factor, times by T, all right? This little t, remember, is some sort of time, either in seconds or minutes or days, okay? So this is what happens. We've got ourselves the lecture examples about a cup of hot tea is allowed to cool in a room of temperature 22 degrees. So it's temperature T, capital T, degrees Celsius, after T minutes. So T has been established, little t has been established in minutes, is given by. Now they may give you that. They haven't actually asked you to formulate that. So this is a question where you're not expected to know too much of the science behind it. It's just a formula. It's an exponential, okay, equation. So here's the first thing. What is the initial temperature? Initial will always mean when T is equal to 0. So if they want to know what it was initially, and you're not sure because you've never seen this before, you simply put the 0 in, okay, 0.82 to the power of 0 plus 22. Now you don't really need a calculator because you should know that anything to the 0 would be, anything to the 0, just remind yourselves of any indice laws out there, is a 1. 78 times a 1, still 78, plus 22. What are we coming up to? Anyone else get 100? 100 degrees Celsius. And you can put the degrees, you can put the Celsius, but you don't have to because that's what we live in. But I would want the degrees sign in there. Okay? So the initial temperature of this hot tea was 100 degrees. How did I find that out? Because I put little t is equal to 0. At the start of this, call it an experiment, all right? Its temperature was 100 degrees. Round 2 says, when will the T's temperature reach 25 degrees? So you've got this down in the second spot. When will the T's temperature reach? When is asking you to find a T value. So I can see that there's going to be another exponential coming up. Will the capital T be equal to 25? So here we go. I'll do it over here. 25 is equal to 78 times by 0.82 to the T, which is what we're looking for, plus 22. Now again, 1, 2, 4, solving equations. 1, 2, 4, solving equations. What do we do first? Because we all know logs is going to appear, but you can't bring in the logs until it's time. Okay? So what should we move first? 22. So we're subtracting the 22. Well, I won't write that. I'll just subtract the 22 and get this. And again, keep your eyes on anything I write up here. I've subtracted the 22. What's the next job to do? Because I so want to do the logs, but I know I can't until it's the right time. Divide by 78. And every single step I do here, I'm just showing it, 0.82 to the t. Now 3 divided by 78. If it simplifies, I'll be happy. Otherwise, I will just be leaving it like that. Now I get a 1 on 26. Anyone else simplify? A 1 on 26. Now I'm not going to write the decimal because the decimal has a really long version, and unless you write everything out, it's not of any point. So you know it's on the calculator, you're leaving it there, but when you're writing it, you can write something a little easier. You're going to bring in the word log. So this is the log of this fraction will equal the log of 0.82 to the power of t. The reason why you've done the logs, why you've brought the logs in, keep reminding yourself because it's from semester 1. And again, this is the log of this. T should equal, I'll get my division ready. I'm dividing by the log of 0.82 and on the top the log of this fraction, which is still waiting for me on my calculator. Now again, if I get a negative answer, I know I'm in trouble because time can't be negative. I must have pushed something incorrectly. So here's what I've got. I've got a fraction, I've got the log of that answer that I happen to have from before. I've got the log of 0.82 on the bottom. All my brackets are complete. Anyone else get 16? 417, ... So it says, when will the T reach this particular temperature? Again, T's in minutes, so I'm just going to finish this question off over here and say T will equal 16 minutes, and again I will tell everyone that I've rounded that off to the nearest whole number. Again, if you go to one decimal place, you're okay to do that. Make sure it's 16.4 minutes. Yeah, I mean, you can get into finer details with minutes and seconds. So when will it reach it? 16 minutes later. And then there's a third part, okay. When will the temperature reach 22? Will. Now you can either say, well, he only wants a yes or a no, but he would say justify your answer. So there's a couple of ways to justify your answer. One way is algebraic. So I'm going to put up here algebraic. Algebraically, here we go. If this was T was equal to 78 times by 0.82 to the T plus 22. How do I do it algebraically? Well, the question wants you to put T is equal to 22 and find out when this happens. Now, I say when this happens. I've got a pretty good idea this is not going to happen. But I need to justify, I need to show Dave why this will not work. And not just because I have this feeling. So algebraically, if you put the 22 in and you go to solve this, what's the first thing we said we were going to do? First thing we were going to do was subtract the 22. What happens when you subtract the 22? You get a 0. Now, at this point, you're still not in trouble at that point. And again, what's the next thing you want to do? Divide by 78. Divide this side by 78. You're still not in trouble because 0 divided by 78 is still 0. So where is the trouble coming? Where? What happens next? Take the log of. What happens to the log of 0? Go and ask your calculator. What does it say to you? Math error. Is it wrong? Do you want to hit it? Do you want to start the batteries, reset it? Is it telling you the truth? Because sometimes we get math error and we know, oh, it's just a bracket, that must have gone wrong. But this is in fact telling me the truth. The log of 0, it's coming up as an error. So can anyone explain to me? We've suddenly algebraically come to the end. There is a problem with this. The log of 0 does not exist. Anyone want to sort of clarify why it doesn't exist? Not just because the calculator said so. Anyone got any thoughts? So over here, this is actually the log of 0 to the base 10. Can anyone think of any number, when you put it 10 to the power of what number gives you 0? Can you think of any number that can be put up there to get you an answer of 0? Because you know 0 can come over here. 10 to the 0 is 1. It's not going to give you that guy there. Put a positive number in. 2s and 3s and 4s. They work, but they don't give you 0. Or try a negative number. What happens to the negative versions? 10 to the minus 1 is 1 over 10. 10 to the minus 1 is 1 over 10. It's not going to give me 0. There is no number I can place here. So algebraically, this has come to the end. Can someone give it to me graphically? So this is algebraically, and then I'm going to ask graphically. How could you have shown that this was never going to get to? Any suggestions? 1, 2, 4 skills from last semester. Try doing a graph. Try doing a graph. So here's the idea. We've established that this is going to be a decreasing. So here's a little graph so far. This is what it used to do. It used to do this, and it used to approach an asymptote. This guy here is the initial value, so it would have been 78. At this point it was 78. but then I got to add 22. So my graph suddenly has a new asymptote and has a new y-intercept, if you want to think of it like that. The whole graph went up 22, so the asymptote went up 22, so now it's at 22. The 78 went up 22. And was that not one of our first questions? Was that not our first question? What is the initial temperature of the tea? Of the tea, as in the drink, the tea. So it should have started at 100. It was coming down. And what is it approaching graphically? What is it approaching? And what will it never reach? It will approach 22 degrees, but never reach 22 degrees is what that is saying. So I will put here, it will approach 22 degrees, but never reach it. That guy there? The graph on that one there, Jackie?
Yeah.
Yeah? Oh, sorry, because you can't see my pointer. This one here?
Yeah.
Yeah?
That's 78, yeah.
Yeah, because all I was graphing was this part of it,
Yeah.
and that was just an exponential.
Yeah.
And do you remember at the very beginning there was some prompts about early work from 1 to 4? There was a 2 to the x, and the y-intercept was 1. And then we put a 4 in front of it. This is on the very early slide. And a 4 times that meant that it went up to 4. That's exactly what happened. This was a decreasing, so it's going down. But instead of it being a 1, because there's a 78 out the front of it, this initial value is 78. But then, if I add the 22, the whole graph goes up. So this is actually the graph of my T. This is the graph of T down here. This was me building it, Jackie. This part here was me building it so I could see where the asymptote was, and then I can see where the asymptote went to. Okay? So here we go. All right. We might just have, okay, I think we'll have our break. We'll do our decay, our radioactive decay, on the other side of that. All right, so we will have our break there. Algebraically, you can prove it won't exist because you get a math error. Graphically, you can prove it as well in this story. So we'll go till 2 o'clock, all right? We will get ourselves with a break. Now, a lot of people might have come in later. Those redemptions, how are we on those redemptions? All right. Well, what happened, Jackie, that you didn't get? As I was saying at the beginning, I know you walked in after, I did say, every time it comes to Friday, if you are at home, and home can be Singleton, Muswell, if I have someone coming in from, you know, if it's too far, scan it and then send it to us. We'll send it to you.
Yeah.
I know you got it.
Yeah, I haven't finished that. So that was the thing, yeah. Because it's finished uni on Friday at 5.
Yeah. So scan it, scan it to do it, scan it to me. Either one. Aside from those, it's not too bad. It does a good job modelling, but there are some problems, you know. So it's like, you know, when people try to estimate things for the future, you know, they've got to model it on something. I was hearing that discussion on Q&A, I think it was last week, they're having a Q&A, and they've had that Brian Austin, that British, is a real scientist, and obviously someone on the panel was on what his name is. It is, and obviously there's always going to be questions and answers what's called that, but there's always this tit for tat sort of argument happening in that guy. Basically, we're still on the thoughts of it doesn't, it's the whole thing of global warming, he wanted to, he actually went around and they, then it becomes part of the music because they catch this guy to show savings as well, so then music picks up on it. And basically, the question is Brian, he's a well-known scientist saying that regardless that's corrupted. And, it's a bit harsh to say that someone who, they've done a lot more than this guy, But he was saying about, collecting data, but you've got to go with something even if it's slightly out, Yeah, that's right, and that's why, it's any sort of statistics, when you do any sort of statistics, or data collecting or analysing, there's always those things hang on about the right boxes. So, that was very interesting, the discussion. But yeah, the guy really wanted to know about his data and how it's modelled. Yes, so I'm going to just do a quick look at this. Is that what you're asking? Yeah, I'm going to have a quick look at that only because we can see that there's only a couple of questions. And it's really just, the main idea is just to it's not a three back-to-back. Well, it comes from, it's going to be up there, so it's quite a detailed quiz. It starts with, it's going to be starting with a formula, and then they rearrange the subject. By rearranging the subject, it's very much what we've been doing here, because this guy is saying derive that to convert that into this, and I'm pretty sure it's just see how we've made it. You basically an exponential equation related to the subject of it. That's what we do in equations. Because that just says derive this to convert its intensity. Yeah. No, not really, no. No, that's just explaining it. But that means all you need is and then this is just saying this has a clarification, all right? This is actually, 100 times more than this, and that's all this is saying. It says clearly, it says you don't have 10 times the power, it's actually 100 times more powerful. It's on the Open Foundation.
Yeah, Tuesday.
Oh, the physics one?
Yeah, the past physics.
Yeah.
Tuesday.
On a Tuesday at
That's 2 to 3 at B106.
V106 upstairs. I'm just curious as to what other
There's a separate one as well.
what other subjects have passed?
Yeah. But they've also just
that all with heat, do you reckon?
That's
The pass wouldn't be.
the pass isn't, but I think so. Well, the Thursday one isn't, but there's a lady who teaches another physics class.
Okay, yeah. All right. Now I'm just curious because normally I would see something pop up if they've just added, just in general, because I like to make sure people know about things or where to find things. And because it's not my area, well, it's just even another way of looking at it sometimes helps. So I'm just going to go to the Open Foundation. I'm just wondering if I'll find. So Nathan, I'm just on the Open Foundation. This is the general. It's just called Open Foundation, and I've just gone to pass. And I'm just interested if they put, see the past timetable? So there's two. Oh, was that first semester maybe then, Jackie? Jacqueline, was that first semester? Because you just called something out and there wasn't that one. Oh, well maybe that was first semester and someone hasn't updated it. Might have been. I'll get back to you, Nathan. I'll go and check with Pete. But you could even just ask at the office, just to clarify, or ask Heath, isn't it? Yeah. And that's interesting, because that might be, if that doesn't sound like yours, Jacqueline, I'd say that might be semester one, maybe. Not much good. Alrighty, we ready? Round two. Oh, these glasses. Round two. Here's what we've got. We've got radioactive decay. So basically what it's going to do is come down. Oh, okay. Check with that one. Here's a radioactive decay. We're on page 58. On page 58, it's again just saying this is one of those exponential functions that is going to get decrease itself in some manner. And again, it's more just the terminology, because you may not have studied a science and never heard of this before, but it will pop up in our questions. So don't be surprised if this story about half-life pops up in your questions for next week. It says the rate at which a radioactive element decays is usually expressed in terms of its half-life. Now, a lot of people may never have heard of that. It's just similar, I say it's similar to the question we just did, where it takes 12 years to keep doubling the population, so it's always the same. A half-life does that, but in reverse. It's always the same amount of time to get half of what you had. So this is what it says. This is the time taken for the amount present to decrease to half of what it had been. And it stays exactly the same. So in theory, it never disappears, because no matter how small you have in your hand some component, half of it is still there the next time. Half of it is still there the time after that. So it never actually goes away, all right, as a simple explanation. So this is basically saying about this carbon-14, and it's just showing you that on this particular diagram it says number of half-lives. The half-life for this particular element says 5,730 years. So for that particular one called carbon-14, it takes 5,730 years to go from 100 to what it was, whatever you have in your hand, to go to half of what it was. So if you started with 10 grams, it takes 5,730 years. And that's particular to that element, say. So this is just showing you how long. This is 3, down the bottom here, this is 3 half-lives. That's about more than 15,000 years, all right, for it to get from 10 grams down to 1.25 grams. Okay, so that's just a bit of an investigation there, because you guys don't have that in your book, okay? So it's going on. So say the half-life of this, it was just telling you about this. Oh, that's right, he goes into his needle up here. Again, we're not going to concentrate on that. It's just a bit of trivia, I guess. He loves his trivia. So don't panic, you're not going to get tested on these equations or anything like that, all right? So don't panic. It's talking about electron counts. Again, he goes through. Again, if you want to stop it, you can watch it and just stop it and then go through it yourselves. But I don't want to put that into your mind that that's going to be in any way examined. It's not going to be examined, so I'll get past him. This is the part we've got, the lecture example. Something like this will come at you. An initial mass of. So again, I hear the word initial and I hear 60 grams. So again, it doesn't matter which letter you use. You can use P's. P's often used for population. When it comes to this, a lot of people use M. It does not really matter what you put there. Okay, so M is equal to M0, and then I'll put times by A to the T. So that constant, that multiplying factor, it says it's decaying by 6% per year. So I'm going to say, I think I know my initial was 60. My multiplying factor was 100%, and it went down by 6%. So it turns out to be 100%, take away 6%, which ends up with 94, which is also the same as 0.94. So I'm going to say my equation could be, and again, don't stress if you use a different letter. You can use A, you can use P, I've got M there, so it's 60 times by 0.94 to the power of T, and I'm just going to remind myself that T would be in years, because that's what the decaying was given to me in, 6% per year. So we've established an equation, and it's meant to be going down. So one of the interesting things is, if you start getting answers that are bigger than 60, it means something has gone wrong, because this has told you at the very start that you are now on a decaying sort of path. So it says what mass, so I will put here, it's asking me for mass, if I tell you that 30 years go past. So 30 years go past, what mass is left? So it says M will equal 60 times by 0.94 to the power of 30. I can tell it's going to be a long number, but it says correct to 1 decimal place. So I always show my original, because if I get the rounding off wrong, all right, I'm hoping that I still get my marks, because I've got this in front of me, dot, 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 and these are in years. And I look up and it said to 1 decimal place. So M is equal to 9.4 to 1 decimal place. And that is in years. 9.4 years for this to... that's not in years, is it, Justin? Justin, what are you going to tell me? That's the mass. So forget that, it's not in years. The mass is in grams. And the mass is in grams. Alright? And the reason I picked that up, guys, I make mistakes, but often what you do is you look back at the question, and when I went to look back at the question, I heard myself ask what mass, and I thought it's funny that I'm answering that in years, and I thought I've done something wrong. And they're the small details you've got to be on top of when you're doing your own corrections. The other part of this question was how long does it take? Okay, how long does it take? So we've got this statement, M is equal to, and we had 60 times by 60 multiplied by 0.94 to the T. So that's just being carried over from the other slide. How long does it take? So how long is asking me for a time. Does it take for the substance to decay to 85% of its original mass? So the mass I'm sort of interested in is 85% of 60. 85% of 60 now. There'll be something pop up when we get to it, but if you do it this way, it's a safe way to do it. 85% of 60, they're asking you, when will it be 51 grams? So again, people might get caught by the words, and they're just saying, well, instead of me telling you 51 grams, I'll put it in another way. When does the substance get to 85% of its original mass? So here we go. We're about to do a substitution. 51 equals 60 times by 0.94 to the power of T. Now you can see again, this is that exponential equation from earlier. So you want to make sure that you're not doing the wrong thing. So the correct thing is to divide by 60. If that particular number is pleasant, I'll write it. It says 51 divided by 60. Anyone come up with an answer and notice anything? Yeah, it's going to be, it's a 17/20. Mine came out as a decimal the first time, so by default mine went to 0.85. So that sounds sort of like why I've got that is because it went to 85%, but I wouldn't have jumped in at that. Most people probably won't jump in at that spot. Take the log of both sides, so this is the log of this side is equal to the log of this side. The reason that it lets you do that, or why you want to do that, is so that the t is brought down by log laws, which was from first semester. To find t, I'm about to divide by the log of 0.94 and making sure that the log of 0.85 is on top. So again, I'm hoping for an answer that's not negative. Again, there's always small places you might make mistakes. So I'm getting an answer of 2.6 something something. Anyone else? 2.6265 ... Question said how long? T was established in years. So this was in years, and your job is, you can round it off. I will go to 1 decimal place, 2.6 years, and I will just say I've done that to 1 decimal place. So it takes about 2.6 years for it to go down to 85% of its original. And it's leading you to that question, okay? It's leading you towards the what is the half-life. And again, not everybody knows about half-life. So what you want to do with a half-life, you can approach it 2 ways, I guess. What it does is it says, what is the half-life? Those words there are saying, find what t is equal to when m is equal to half the original. What was the original sample we had? We had a 60 gram, and it's going to be a 30. Now, a lot of people will go through this. There's going to be a spot where you can go, oh, I see where I could have taken a shortcut. So I won't put that there yet. I'll just put this is 60 times by 0.94 to the t, and I'll just go and substitute in. You get 30 equals 60 times by 0.94 to the t. It's about here that you realise that when you divide by 60, you get the answer, a half. And that's not surprising because you want half of the original amount. So it's not surprising that you see half on a regular basis when you talk half-life. Take the log of both sides. And again, the reason why you take the log is so that the t can come down. So again, you should be getting really good at these exponential equations. I'm dividing by the log of 0.94. You can put that in as a half or 0.5, whichever one you would like to have. Top one is the log of 0.5, bottom one is the log of 0.94. I'm getting about 11.2. Anyone else? 2023 ... But that just gives you an idea if you're on the same sort of page as I am here, the same spot. It then says, look, we'll round it off to 1, so 11.2 years, and again I'll put to 1 decimal place. So it takes 11.2 years for it to go from 60 grams to 30 grams. It takes 11.2 years for it to go from 30 grams to 15 grams. It takes 11.2 years to go from 15 grams to 7.5 grams, and so on, all the way. Question is, will it ever get to 0? And in theory, by this equation, it never does. And it's the same thing. You could do it algebraically, and you can do it graphically. This, again, has an asymptote, and it's approaching 0. It just never reaches 0. It gets really, really small. So then, it says here, now, he put down, he hasn't got this in the book, but he's got these questions here. And it's like a multiple choice, so he just wants you to read, because it's just a simple question if you understand the idea of half-life. Find the half-life of a radioactive substance which decays according to this equation, where m is in grams and t is in days. So what is the half-life? Okay, so what would you be doing? All right, to figure this one out, what would you do? What would you do? Now, he hasn't got it on this, so if you've got a spare sheet of paper, because he's actually put some spare questions in here before we get to the Richter scale, so you might want to jot it down, or you might just want to look back at it. It'll be on the recording, so even if you don't get to write the whole thing down, just go to the recording at round about whatever time, an hour and 15 into the recording, so you can see the questions that were put up there. So you want this M to equal, you want it to go down to 100. All right, so half of what it started as. I can tell it started as 200, by the way, because that's the initial amount. All right, so again, you're going to be putting the 100 in. You know that at some stage you get a half is equal to 0.5 to the t. Now, I don't actually need logs for this one. Do you know why I don't need logs? This says 0.5. This says 0.5 to the t. Missing number up here would be to the power of 1. So t is equal to 1. What was t actually in? So again, t was actually in days. So it turns out to be 1 day. It takes 1 day for this particular substance to halve itself. So every day goes by, it halves and halves and halves. All right? He also has a group of questions here. Again, this is not in there, but you might want to go back and again just see the style of question. Get used to it. You get them in your tute as well. Find the half-life. So again, I'll just set this up. It's asking you for the t value, which decays according to this particular equation. Again, this was the initial amount, so M0 is 200. M0 is 200. And you want to know when is M half of that. So the question is, find when t, what t is, for M to be 100. All right. And again, I'm just going to leave that one. It's the setting up. I think we've done quite a few of the questions. This one here says, find the doubling time of a population growing according to this. Now, this is growing, and we want the doubling time. So it's not a half-life, but how long, find how long it takes for the population to double. So how do you know where to start on that? Well, if the initial population was 24, and again I can see that because that's what that stands for, the initial population. The question is double it, make p equal to 48, and then go and find how long. Again, it's another exponential equation. We've done it a fair few times. All right? So that one there you can go and investigate. This one here just says it's reminding you of some log laws, okay? Just a reminder of some log laws and how you make, this is called index form here. This statement is in index form, this is in log form, and they mean the same thing, or they say the same thing, all right? And then it was reminding you of the log laws. We've been using this one quite a bit in our equations, that's why we had to pick it up. And this one down here is just reminding you of a change of base. So change of base law, which might be needed. Now he's put that there because then he goes on to saying, where do logs get used? Now you won't get examined a great deal on this next section. It's going to be quite a lot of slides here, but it's just informing you. One of the main areas we use these logs, okay, is with the Richter scale when earthquakes get measured. So it says a logarithmic scale is a non-linear scale. So it's non-linear scale. So you know when you used to put your x and your y axis up, all right, that's a linear scale. When you make it, you get the dots together, you join it, and you get a straight line. So it says a log scale is a non-linear scale used when there is a large range of quantities. So a large range of these quantities. So it goes from a really small number to really, really huge numbers. And you can't plot it on a normal sort of axis because you wouldn't be able to get it all in. You wouldn't be able to fit it in. It's based on orders of magnitude, so there is the important bit on the orders of magnitude rather than a standard linear scale. All right? So again, it's just going to go through this idea that if you have, this is a log to the base 10, by the way, if you don't see the base, all right? So what would be this guy's answer? What's the log of 10 when you're on a base 10? So you can use your LOG button for any of these because that's what the LOG button is to the base 10. Otherwise you should know them anyway. What do you get for this guy? You get log of 1. This guy here is the log of 100, and when you're in a base 10 the answer is 2, and then 3, 4 and 5. Alright? So what it's doing is, just as a simplified version, if you had to draw a scale that had to start with 10 roundabout and get to 100,000, you'd find it very hard to put on your scale because you're going, well, I've got to show a dot at the 10 spot and I've got to also show something at the 100,000. So this is why this log scale does this little bit of, I don't call it, it's not magic as such, but what it does is it turns it around so you don't have to go, oh, how am I going to fit that all in? So you've got to be careful to watch the actual scale. It won't say X and Y, it'll say X and the log of Y if you're going to look at it. Alright, so over here, this would have been the linear scale, and if you were trying to fit these in, you can see that it's got the first one fitting in, it's got the second one fitting in, it's got the third one fitting in, but then after that, you know, we need more. We need it a lot more. So then what it does is it says, what if you went to this and it says semi-logarithmic, and again, he's just plotting. Again, you can see them trying to fit, oops, it's trying to fit all of these in. Okay, so he's gone to this slightly log sort of scale, and then on your page 59 he starts talking about this Richter scale. Again, you don't get examined a great deal, there's just a couple of calculations we have to get to. It's talking about who invented it, and that's why it's called the Richter scale. It's used to rate the magnitude of an earthquake, which is the amplitude of the ground motion recorded by the equipment called a seismograph, also taking into account the distance from the actual earthquake. Now, the Richter scale is actually in logarithms, okay? It's logarithmic, meaning that a whole number increase in the scale relates to a multiplication of 10 times in the earthquake's magnitude. Alright, so you can see that he's got, alright, he has got this written down next to his graph, next to that picture of the Richter scale. He's got that. So when you hear a Richter scale of 5, it's not really a 5 but a 10 to the 5. Alright, and it's saying that if you heard someone had a earthquake of magnitude 5 and you heard someone had one of magnitude 4, the first thing you do is think, well, this sounds like it's, you know, one difference, but it's actually 10 times greater. Alright, because this is actually a 10 to the 5, this is actually a 10 to the 4. And if you said how much greater is it, you do a division of 10 to the 5 divided by 10 to the 4, and you get a value of 10. So it's saying, now these are pretty much about the only questions you'll get on page 62, say things like, what is the difference in magnitude of an earthquake? So you just have to be able to figure out, how do I know how to calculate the difference in magnitude? So I'll say this again. You can put it there next to your page 59. We're about to do 3 of them at the bottom. Okay? So it says down the bottom there, we get to our examples. There's the diagram. This one here is your first one for the lecture. What's the difference in magnitude of an earthquake if it says a Richter scale of 5 and a Richter scale of 3? Most people will jump to the answer of 2, but it's not actually. This is actually a 10 to the 5. This is actually a 10 to the 3. And when you want to know what the difference in magnitude is, you do a division. So it's a 10 to the 5 divided by a 10 to the 3. All right, you get a 10 squared if you want to use your actual indice work. So it would be 100 times stronger. So an earthquake, stronger. An earthquake that you hear the number 5, you hear the number 3. It doesn't sound like there's much difference, but it's 100 times stronger. So fill that in on the lecture example. Try the next guys out. I think it comes up on our next slide. A 4.5 and a 4, and then it's got a 5.5 and a 5. So I would just get this out to say this guy here is a 10 to the 4.5. This one here is a 10 to the 4, and what I did was I put the bigger one divided by the smaller one. So have a look what happens on that one, and the same for this guy here. This guy will be a 10 to the 5.5, a 10 to the 5, and then notice what happens when you do the division on this one. So tell me an answer that you get from your calculator when you do that division. It's not a pretty number, so it keeps going. So I've got my 10 to the 4.5. Underneath it's my 10 to the 4. Did you get an answer of 3.16? Anybody? Anybody get that sort of number? 3.16 ... So it doesn't sound like much in the Richter scale or on the Richter scale, but it's still 3 times stronger. Okay? And when you do this, you end up getting the same answer, 3.16. So just check it for me that you get the same answer on those two guys. So that's the type of question you'll get. That's it. On page 62, all I see in the actual tutorial is just to do some comparisons. And the very last thing we have to discuss is this decibel scale. This decibel scale, okay, pops up here. This is still the Richter scale, and you put in an extra table. You don't have it in front of you, but it's just saying how things sound a lot worse, or how they are actually a lot worse than what they sound. The decimal scale. Now, you probably, you've never really stopped to think about it. You hear people talk about decibels, and, you might be in a job, or someone you know might be in a job that has, a hearing problem because of their, experiences in their job. Something has happened. And when you actually go through this table, all right, it's really quite astounding that you hear what's about to come out in terms of comparing things. So it just goes on to say, I'll just go through a couple of the smaller details, which are that humans are equipped with very sensitive ears capable of detecting sound waves of extremely low intensity. Again, this isn't a science lesson, so you hear just a little bit of, low intensity, really, really low intensity, and we can hear it. The faintest sound that the typical human ear can detect corresponds to a sound that would displace particles of air by 500 millionths of the width of a human hair. So it's that size there. And it comes up on your table as the very top number. So 1 times 10 to the minus 12, okay? And it says that there is actually going to be, see how it's got threshold of hearing? So it's got a TOH. So things will get compared to this threshold of hearing, all right? So then it goes on to say the maximum sound a human ear can safely detect without suffering any physical damage is more than 10 to the 12 times more intense than that. So if you run your fingers sort of down the right-hand side, can you see that column, okay? So I'm just waiting to see where he's got that column there, that table. So you can see that the threshold of hearing has come in at that number there. That's the intensity. And it's been allocated the 0 decibels, okay? When you hear something like rustling leaves comes in at this intensity, and this intensity comes in at 10 decibels. So 10 decibels sounds like 10 times more than that other one, okay? So this here is 10 times stronger. So this is 10 times more intense. I'll put not so much stronger, but more intense. Sorry, I can't fit that in there. More intense. So when you get to a whisper, the whisper now, look at what happens. This number here comes out to be an intensity level of 20 decibels. 20 decibels sounds, well, it sounds like it's twice 10. But in fact, in terms of the number of times greater than that threshold, it's actually going to be 100 times more intense than that threshold. All right, 100 times. The next one will be 1,000,000 times. So normal conversation is 1,000,000 times that normal, that what they call the threshold of hearing. And remember, at the very beginning, they said that threshold of hearing was extremely low, was an extremely low intensity. So even just reading through that, again, you're not going to be asked to call up any of that, to memorize any of that. You can see that the only questions on page 62 is you comparing the difference in intensity all right, of these two particular things. And so I've just got to get through one more bit, which is at the bottom. See the derive? Again, I would not worry too much. I would just put down when I get to this, this one here, which is going, this is just leading up. This one here, what intensity? So see this guy here, all right, that is actually saying the number of decibels. So I will put here that the number of decibels is calculated by saying 10 times the log. So I'll put 10 times, I'm just rewriting it, but you may think that that's a 1 up there, but that is an I for intensity. So this here is your intensity up there, and it says over 10 to the minus 12. So you can figure out the number of decibels. So if you go back to that table, you can figure out the number of decibels, the answers that are in the third column, which are all in decibels, if you know the intensity. So this question here says, I can tell you the number of decibels. Oh, did I put decimals? Having a shocker. Decibels. Oh, number of decibels. All right. 10 times the log of. I think I should be at home. Maybe Dave and I, he maybe sent me an email, told me to stay home today. I didn't read it. So this tells you the number of decibels if you know the intensity. All right, if you know the intensity. Now this is just going through an example here just to convert 105. All right, so it's actually putting 105 on this side, and then it will go through. What this is doing is it's making, it starts with that formula, and it's going to be making I the subject. So I will put here, making I, which is intensity, making intensity the subject. So if you look at it, it's really just what we've been doing over and over and over again. We have been finding, all right, we've been finding equations where we've been trying to solve it for one of the variables. Your job here is to make I the subject, okay? So for you to make I the subject, this is again a little bit of 1, 2, 4 work. How do you work backwards? So there are two variables. There's this variable and there's this variable. And if you want to make I the subject, the first job would be to divide by 10. So that's what disappears on the first line. How do you remove a log, or how do you write it in reverse? Again, that's from 1 to 4 when you go from index form to log form. This is log to the base 10. So if you want to remind yourself, there is the base. And that's why on the next line it says 10 to the power of what's on this side. 10 to the power of 0.1 dB is now equal to that answer. So remember, when you used to do logs, you used to have it in index form and then you'd have it in log form. I'll put a little example down here in simpler. If you have 2 to the power of 3 is 8. When you convert that, that's in index form. When you convert it, you put log of 8 to the base 2 is 3. That's changing its format. That's exactly what's just happened there. And the last line is to multiply by 10 to the minus 12, which is what they just did there. And then if you're wondering, this line here, because they had the same base, you could add these indices. Remember some index laws? All right, so they added those numbers there, or added those terms, and then it just got written round the other way. So this guy here says I can find you the intensity. Now that I've made I the subject, I can tell you the intensity if you tell me how many decibels you have. Have I made another mistake in there? No? Were you going to ask something? It's just the reverse of, this is called log form. This is log form here. And this is index form. And really when you say you get rid of it, what you're doing is changing it from log form back into index form. Okay? And I'm just pointing out this formula. So even if you just write the answer at the bottom of page 60, you make this equation appear. I is equal to, and then it tells you what it is. Because on page 62, find the difference in intensity. Your job will be to find the intensity of 20 decibels, what it converts to. Now the 20 and the 30 are already on the table. So the 10 and the 20 are already on the table, but 30 is not on the table, 45 is not on the table. 1's not on the table and 2's not on the table. So on page 62, the couple of questions you've got using this, all right, you'll need that conversion. You'll need that formula to be able to do it. Now, before you leave me though, I'm just going to point out the chute is very small, but I need to point out one thing in the chute. So I'm just going to, when you're ready, I'm going to take this off. I just need to show you the visualizer. Okay, so once that's up, everyone got that formula because you definitely need it for your exercises. I definitely write it down. Again, I'm not going to test out, do you know the intensity of a vacuum cleaner. I'm not going to ask you that. Can I turn this one off now? All right. So what I would do is just move this out of the road for a second, and I will put the visualizer on because I just want you to make a note in your actual books. Can you go to page 61? On 61, let's have a look here. Let's zoom in there. All right, see 61. Now, there's not a lot to this chute, okay? There is not a lot to this chute. I might end up putting some extra questions up on Blackboard. However, a lot of this has got you constructing, so let me just highlight these. I can see the word construct there. I can see the word construct on most of these. Now, it then has down in number 6 and number 7, it's got an E appearing. Can you see the E to the power of? Can you see the E to the power of? And I think it's on the next page on question 8 as well. So, see those guys with the E's? What log button must you push on those questions? Which one must you push? Log to the base E, which is log to the base E, which is otherwise known as ln on your calculator. If you don't push ln, you're using log to the base 10, all right, which would have been okay before, but I'm pretty sure these ones here you may go astray. So before I get sent any emails, I thought I'd tell you it's on question 6, 7 and 8, all right, 6, 7 and 8 because the E number has appeared. And then as I said, exercise 5.4 is just a little bit of figuring out the difference in magnitudes and the difference in intensities. Alrighty, so if you've got any other questions, otherwise get those redemptions in, guys. Get those redemptions in. Go past the room if you need to print one out. You don't want to pay for it. They're up in room, what's that, 42, I think, down the bottom. Don't kill your calculators yet. Take care, guys. Thanks, Jacqueline, for that info on pass as well. Take care, Nathan. Anything you want to ask, any extra bits, or are you able to get to any? I know Jason, did you get to some clinics? Or the droppings? Yeah?
On Tuesdays, Fridays.
They work for you? Okay, because I'm in there on Thursday, so I just said, has Nathan been? He said, yeah, you had, so that's good.
I can make it Thursdays, but I feel like wait an extra hour.
Yes, you don't.
Got,
It's only when there's a period where you might say, maybe this week I might.
yeah, I've only got the tutorial today, so I can just go home after.
Yeah, that's fair enough. But you know that as we get closer to that bigger test, if you know you want to. See ya. Thanks. Thanks, Cassie. Yeah, just to make sure. That's it. See you, Nathan.